Welcome to The Explainer. Today, we're going to decode something that, well, pretty much runs our entire digital world, the IP address. It's the hidden foundation for everything we do online. And once you get it, you really start to understand how the internet actually works.
So here's what we've got lined up. We'll start with a super simple analogy. Then we'll break down what those numbers actually mean. After that, we'll see how we organize them, why that's so critical for security, and then we'll take a peek into the future.
All right, to really get a handle on this, let's kick things off with a simple idea that makes the whole concept just click. Think about it like this. If you want to get a letter, it needs your home address, right? Well, it's the exact same thing for the internet. Every single device, your phone, your laptop, even your smart fridge, if it's connected, it has an IP address. It's that unique identifier that lets devices find each other and talk.
And this is where it gets really clever, with two main types of addresses. Your Wi-Fi router at home, it gets one public IP address from your internet provider. That's its street address for the whole world to see. But then, inside your house, it acts like a building manager, handing out private IP addresses, like unique apartment numbers to your laptop, your phone, and your TV.
Now, let's pop the hood. Those numbers you see, like 192.168.1.1, they aren't random at all. They've got a really specific structure that computers can read perfectly.
So while you and I see four numbers separated by dots, what your computer actually sees is a long string of 32 ones and zeros. This long number gets chopped up into four 8-bit chunks, and we call those octets. Each one of those octets gets translated into the numbers we're used to seeing, anything from 0 to 255. Okay, so how does that translation happen? Well, each of the 8 spots in that chunk of binary code has a fixed value. You can see it here. The one on the far right is worth 1, the next one is 2, then 4, 8, and you just keep doubling it all the way up to 128 on the far left.
So here's the magic trick. The computer just looks for which of these spots are turned on, which ones have a 1, and it adds up their values. That's it. So in this case, it sees a 1 in the 128 spot, the 32 spot, the 8 spot, and the 4 spot. Add them all up, and you get 172. Simple as that.
Okay, this is super important. Every single IP address is actually doing two jobs at once. The first part of it, the network portion, is like the street name. Every single device on that network shares the exact same one. The second part, the host portion, is like the unique house number. That's what makes your device special on that street. And that is the million-dollar question, isn't it? How does your laptop or your phone know which part of the address is the street it lives on, and which part is its own unique house number? Answering that question is the key to organizing the entire internet.
So how do we solve this problem? Well, the first attempt was kind of clunky, but it didn't take long for it to evolve into something way more flexible and a whole lot smarter.
The original way was called classful addressing. It basically carved up the internet into these huge, rigid blocks called Class A, B, and C. The problem was, if your company needed, say, 300 addresses, you might get a Class B network with over 65,000 of them. It was just incredibly inefficient and wasted millions of addresses. And you can really see the difference here. Over on the left, that's the old, rigid system where the line between network and host was always in a fixed spot. But now look to the right. That's the modern way, where we can draw that line pretty much anywhere we want. And this new, smarter system is called CIDR. Instead of those clunky classes, it uses something called a subnet mask to tell a device exactly where that line is. So when you see something like a /24, it's just telling the computer, hey, the first 24 bits are the network, and the rest you can use for individual devices. This lets us create networks of any size we want, which is just way more efficient.
So this whole idea of flexibly dividing up networks, what we call subnetting, isn't just some abstract technical thing. It has massive real-world consequences for how our networks perform, and maybe more importantly, how we keep them secure.
And check this out. Here's a perfect real-world story. This network admin at a government agency was literally running out of IP addresses. The network was full. So what they do? They just tweaked the subnet mask from a /24 to a /23. That tiny change instantly doubled the number of available addresses. Problem solved.
But making room for more devices is only half the battle. Today, one of the most powerful uses for subnetting is actually cybersecurity, all thanks to a strategy called network segmentation.
The logic here is simple, but it's absolutely brilliant.
You take your big network and you chop it up into smaller, isolated subnets. You put your sensitive financial data in one, your guest Wi-Fi in another, and employee computers in a third. Then you stick firewalls between them. So if a hacker gets into the guest Wi-Fi, they're trapped. They can't get to the important stuff. It contains the damage.
Now, for all its clever tricks, the IPv4 system had one giant, fatal flaw. We ran out of addresses. Seriously. The 4.3 billion addresses it had just weren't enough. So, the world needed a massive upgrade. And here it is. Say hello to IPv6. Right away, you can see this isn't a small step up. We're leaping from a 32-bit address to a 128-bit address. We're moving from simple decimal numbers to these longer hexadecimal ones. The scale is just mind-boggling, and it even comes with cool new features like auto-configuration to make managing networks easier.
Yeah, that number, that's 340 undecillion. It's so big it's basically meaningless. It's enough addresses to give every single grain of sand on Earth its own IP address, and still have trillions and trillions left over. The bottom line is, we are not running out of these. Ever.
So that brings us to the really big question, doesn't it? This nearly infinite new address book isn't just for more computers and phones. It opens the door for everything to get connected, from tiny sensors in our cities to medical devices to every appliance in your home. It's going to change our world in ways we're probably just beginning to imagine.